And a screen share. Okay. And let's go to our notes. You guys are not interested in periodic trends, I don't think. So let's start a new set of notes. And it's the 21st, correct? All right, so I may actually end up keeping you guys all that long today because really what I want to go over is basically how we're going to set up the Excel analysis for the glucose analysis that you guys did last night. By the way, given that we didn't get to use the plate reader and we had to kind of fall back on the Spec 20s, I thought the lab actually went pretty well. The good news for you guys here is that since you don't have to deal with large amounts of data that normally you would have to deal with when you're dealing with the plate reader, it's going to very much simplify the whole Excel and data workup process. So it's not going to be anywhere near quite the task that it would have been had we actually used the plate reader. The nice thing about the plate reader, if we'd been able to use it, is it gives us replicate data for all of our different trials. So for all of your unknowns, for every single standard that we run, we could have gotten 5, 6, 8, 10 different replicate measurements of each one of those things. And that's really nice because then we could calculate means and standard deviations for all of those things. We could put error bars on our plots and have a lot of information also about the unknowns. But we weren't able to do that. So hopefully everybody did get replicate measurements of the unknown. Doesn't matter if you did or didn't do that with the kombucha. The kombucha is really more for my edification than yours. Just so I know that if I want to tweak that experiment for next year and use the kombucha again, we can do that. So data workup is going to involve two different things. And we're really going to kind of focus on the Excel part of it, how we would actually do this in Excel. This lab, any which way we do it, really lends itself nicely to using Excel. Part of that is because obviously Excel is a very good graphing program, so you can make a standard curve with it, which you guys have already done with the kombucha alcohol analysis lab. Most of you actually did it with the kombucha acidity lab. And then I think everybody also used it in the last lab, which was the iron analysis. So you should be getting pretty good at making graphs with Excel. I think pretty much everybody came in knowing how to do that. All right, so two parts to the experiment. The first one, of course, is going to be the standard curve and unknown analysis. All right, so remember what we did with the Spec 20. Basically, we got a bunch of absorbances for a series of standards, and we were able to or are going to make a standard curve. Now, it's Beer's Law plot, pretty much just like the iron analysis was, where basically we're going to be measuring absorbance on the y-axis, and your x-axis is going to be parts per million of glucose. Okay, so these are for your standards. Now, I think you're going to have a total of 5 data points here, right? Starting out with the blank. Now, here's something to keep in mind. The blank is actually a valid data point. You measured it. Okay, so when you actually blanked your spectrometer, you set the transmittance or percent transmittance to 100%, which means 0 absorbance. So that's a data point that you actually collected. So you might as well plot it. Okay, and then I think you had 4 other data points in there as well. So you're going to have a total of 5 data points. Hopefully they fall on a straight line. Okay. Now, how linear this curve is going to be is really going to depend not so much on the ability to make a good measurement with the Spec 20, but how well you did pipetting when you actually made up the unknown solutions. So this is where we get to see how well you really use a micropipette. So we'll have our 5 data points here. And of course, we're going to use Excel to fit a best line through them. So it should look something like that. So you guys know that Excel will give you the equation for the best fit line, y equals mx plus b. So it's going to give you m and it's going to give you b. The other thing that you guys know you can get is an r squared. Okay, that's the correlation coefficient. And the closer to 1 that is, the more linear the fit. Okay, the better the fit. All right. And again, I'll make a note here, since that you only really took one absorbance measurement for each of the unknowns, there are going to be no error bars here. It says in the procedure, obviously, to put error bars in, but that's because we used the plate reader, which we didn't do. So you can't put error bars in there because you only got one set of measurements. All right. So here's something that we can think about in terms of Excel. Obviously, what you would have here is a set of X data, which would be your parts per million glucose, and a set of Y data, which would be the absorbances that go along with. But I know that a lot of you guys ended up taking your measurements, not in absorbance, but in percent transmittance. Okay, so maybe you did it both ways. Maybe some folks did absorbance, maybe some folks did percent T. All right, but here's where Excel could be useful to us. Now, again, just to review what an Excel spreadsheet would look like. Okay, so what's going to happen is you're going to end up with a grid there, as you guys know, and you're going to have columns, which usually have A, B, C, D, whatever. And then, of course, you have numbers going up and down, 1, 2, 3, 4. All right, so your typical spreadsheet's going to look like that. So, of course, you're going to have, it's like Battleship, right? You're going to have an address here. Okay, so if this is going to be position 1 under A, we would call that cell A1. Okay, so this guy would be B1. And of course, if we came down here, that would be A2. And this guy would be B2. So as you guys know, every cell has an address associated with it. All right, so the nice thing about that is if we can utilize an address here, what Excel really does, in its most powerful form, is that it can do repetitive calculations. And of course, most of you have probably used it to do that, but I'm guessing that some of you may not have. So Excel has tremendous capacity beyond just being a graphing program. All right. So for example, let's come down here and say that we ended up with data that looks like this. So over here in column A, I can have column B, I can have column C, and then I can go down. I can go 1, 2, 3, 4, 5, 6, however far down we got to go. Okay, so let's say, for example, we're going to have this as our standard in ppm. So one thing that's always good to do in Excel whenever you're setting things up is to label what you have in a given row or column, right? So if we want to do this by column, we could let A1 here just be standard in ppm. So we could just label that, okay? And then under it, we could actually put our standards. So we have a 0. These are parts per million glucose. What were the other ones, like 20? I think one was 40, one was 60, one was 80. And then under that, we've got your unknown. So you'd have 4 values of your unknown. So you could have, for example, your unknown 1 would go here. So we'll just put, and then you get the idea, 8, 9, and 10 would be your 4 unknowns. And then you could put the kombucha under that as well. Okay. So you have a set of standards or what have you under that. Now, over here in column B, let's say you did percent transmittances. That's what you actually recorded. Okay. So let's just throw some numbers in here. So if the blank was 0 concentration of glucose, the percent transmittance of your blank should have been 100.0, right? You set it there. So that's what it is. And I'm just going to throw some numbers in here. Let's say your 20 part per million gave you 85.3. Say your 40 gave you 60.1. I'm just making something up. I have no idea whether this would be linear or not. 40.3 for this guy. And then we could have like 20.1. And then, for example, we could say that your percent transmittance for your first unknown, I don't know, let's just make something up. It was 41.3. And then if we have 8, 9, and 10, you'd have unknown 2, unknown 3, and then unknown 4. Right, and these are all replicate measurements of your unknown. So let's say then this one was just 41.2, 41.3, and let's just say this is like 40.9. Okay, so those would be your replicate measurements of your unknown. And then you can put your kombucha down there as well. All right, so here's what we could actually do with this. Now, let's say, for example, I want to get to absorbance because that's what I'm going to plot up here, right? I want my plot to be absorbance versus ppm glucose. So I need my Y values. So I could put absorbance up here under C, okay? Now, here's what I would do. We know how to get from percent transmittance to absorbance, right? We know that absorbance is equal to the negative log of the transmittance, okay? So here's what we could do. We could take this cell right here, okay? And I want that to be an absorbance value based on a percent transmittance measurement. So this is how we do it. And I think you guys all know how to do this. I hope you do. But if I want to actually program an equation into this, I can do it. And I do it by sitting inside of that cell, which is what? C2, okay? And I'm going to set it equals to, and you always have to put the equal in there. And we're going to tell it to convert transmittance to absorbance. Okay, so I've got minus log. Okay, but where is my percent T value that I'm going to work with? Oh, that's over in column B, isn't it? And does it actually have a does it actually have an address? Yes, it does. It's B2, isn't it? So it's the negative log of, and we can do this all in one fell swoop, B2, right? Because that's where my percent transmittance is, that corresponds to the absorbance I want to calculate, divided by 100, right? Because I want to undo the percent. So I could do that in one fell swoop, just like that. So then, if I actually tell it to do that, guess what? It's going to put a value of absorbance now in cell C2 that corresponds to the percent transmittance in B2. So does everybody, have you guys all done that before? Program cells like that to actually make, have Excel do math for you? Has anybody not done that? Sounds like pretty much everybody has. Now, if I had done this 10 years ago, half the class would never have seen this, okay? But I think at this point, you guys have done enough with Excel in high school and maybe presently here. Everybody hopefully knows how to do that. Okay, so once you've got it, right, what are you gonna do? Then you're just gonna copy down. So you're gonna copy that cell, C2, you're gonna, and then paste down. So you're gonna copy and paste down. Now, the nice thing about that is then that takes every subsequent value of percent transmittance. So if you're over here in B3, okay, and you want to see what absorbance C3 is going to have, when you copy down, it automatically takes B3 and sticks it into that equation. Okay, so if you're talking about B4, it takes B4 and sticks it into that equation and puts that into C4 for you. So that's where Excel is really nice at doing repetitive calculations, so you don't have to do them, okay? So otherwise, you know, if you had all these different ones to do, and so you had like 10 different ones, 11 if you had the kombucha, if you had to crank that out 11 times on your calculator, that's going to take time. But if you just program it into the cell and do a copy and paste down, you're done in a second or two. Okay, it's that simple. All right, so that's how we can actually use Excel to do repetitive calculations. And this is just a simple example of how we might do it, just to help us to get from percent transmittance back to absorbance in your standard curve. Okay. All right. Any questions about that? And again, I'm hoping everybody's done that before, but if you haven't, or if it's been a long time, okay, then this is how you do it. As a matter of fact, where you might have done this before is back when you were calculating that first derivative plot for the acid analysis. This would have been a perfect time to set up an Excel spreadsheet to do this kind of stuff. Now, the reason I mention it now is because I remember going back into that experiment and seeing that some people did that, but there were some people who just did, it seemed like hundreds of calculations by hand when Excel could have just done it all for you. Okay, so that's why I want to make sure you're aware of doing this. All right. So that takes care of the standard curve. Once you've got your equation for the best fit line, do the normal thing. For each one of your unknowns, okay, plug your absorbance in and into the equation for the best fit line. And heck, you could even get Excel to do that for you, right? You could just take the equation for the best fit line, plug it into Excel, and have it solve for the variable you want, right? So you could even have Excel do that instead of doing it 4 times by hand. So that's totally up to you. All right, and then you've got a mean, a standard deviation, 95% confidence limit like you normally would. Now, the second part of this thing, is everybody okay with the standard curve? Any questions about that? Sipping my kombucha here. All right, so the second part of this is actually the kinetic part. Okay, so let's remember what we're doing here. We're trying to use the method of integrated rate laws to determine from time-dependent concentration data what the order of the reaction is, okay? And then once we've got the order, then we can get the pseudo rate constant for the reaction from the slope of the plot, okay? So you did this back in dynamics, back when you did the rate stuff. So this is just a way of getting at an order and a rate constant using time-dependent data. All right, so let's think about what we actually have to do. So let's say, for example, we want to make a 0 order plot. What you're going to do, you're going to do a 0 first and second order plot. Now, we kind of talked about this last time. We said that the 0 order integrated rate expression looks like this. And let's just do it in terms of glucose. It would be glucose at time t is equal to minus K times T plus the concentration of glucose initial. Isn't that it? All right, so obviously what we have is something here that's in the linear form, y equals mx plus b. So if we have a 0 order reaction, what are we going to plot to test? Well, we're going to plot, okay, the concentration of glucose as a function of time. So that's going to vary, right, as a function of t. Now, the sign here says we should get a negative slope for this. So if we have a 0 order reaction, what we're going to get is a straight line with a negative slope, okay? And what do we know here? We know that the slope is going to equal to minus K, which is my rate constant, right? And you can tell here what the units of the rate constant ought to be from the slope, right? So it looks like it ought to be molar per second, right? Rise over run. So molarities on the y-axis, times on the x-axis. And it's fine here if you want to actually go ahead. You took your data in minutes, right? So it's fine if you want to go ahead and do this in terms of minutes. Okay, you don't have to convert it to seconds. It just means the rate constant would now have units of molarity per minute instead of molarity per second. You could do it either way. Okay, the trend should be the same. All right. So that's a 0 order plot. Now, obviously, if we do a first order plot, what are we going to plot? I think we talked about this last time. Well, in this case, we're plotting the natural log of the glucose concentration as a function of time. It's time dependent. That's going to equal to minus KT plus the natural log of the initial glucose concentration. Okay, so that's y equals mx plus b. So if you've got a first order reaction and you plot out the log of the glucose concentration versus time, you're going to get a straight line with a negative slope. What does second order look like? That's the 1 over the concentrations. That's the inverse, so it's 1 over the concentration of the glucose at time t is equal to positive KT, so it's positive 1 this time, plus 1 over the concentration of glucose initial. Okay, So again, y equals mx plus b. So if you plot this out as a second order plot and it's linear, okay, that tells you that your order with respect to glucose is second order. Okay, so you're going to plot this out three ways. The one that gives you the most linear result will be the order. Okay, so everybody clear on that?
Yeah, but I have a quick question. The lab says to get molar absorptivity by using the largest value. So should we use our value at 30 minutes and basically assume that that's the endpoint of the reaction?
Yep.
Okay.
In a short number of words, yes. So we're going to get there. Okay, so notice that no matter what we do, we need to have the time-dependent glucose data. Okay, now what are we talking about here? Okay, well, we're talking about the amount of glucose or the concentration of glucose that is left over at any given time, right? So let's think about this. So glucose at time t, right, is going to always equal to the concentration of the glucose initial minus the concentration of the glucose that got used. All right, so this is left over. What's left? That's what we're plotting. All right, so in order to get at this, what do we need? Well, we need the initial glucose concentration, but we also need to have a way of measuring the concentration of the glucose that got used. All right, and the difference between those two is always going to be the glucose concentration left over. Now, here's the deal. If I want to get the glucose initial, right, I can calculate that because we know what we started with, right? And everybody started with the same thing. So this is a calculation that's going to be the same for everybody. So let's think about it. So the procedure said to take 50 microliters of glucose. Okay. Now, what we're going to do is recognize that that was parts per million, right? So what did we have? We had a standard that was 1,000 ppm. Okay, so 1,000 ppm is the same thing as 1,000 micrograms per milliliter, which I could write as 1,000 micrograms of glucose. And since we're in microliters, let's just go ahead and say that a milliliter is equal to 1,000 microliters. Okay. So microliters will cancel with microliters. We got micrograms of glucose. Let's convert that to grams because we got to get everything in terms of molarity is basically what we're trying to do here. All right, so we know that 1 gram of glucose is the same thing as 10 to the 6th micrograms of glucose, right? So micrograms will cancel with micrograms. Now I can use the molar mass of glucose to get me to moles. All right, so I know that for every 1 mole of glucose, the molar mass is 180.16. Okay, so grams of glucose will cancel with grams of glucose. Now, the last thing I have to do is divide this by the diluted volume. Okay, so what was the total volume in the big test tube? Well, if you add everything up, it was 3 milliliters. Okay, so ultimately I'm going to now multiply this by 1 over V total. And if I'm in terms of moles, I'll go ahead and put it in terms of liters. That would be 0.003000 liters. Okay. So we can say here, and I'll just run it out to 3 sig figs total. There's no real reason. It's probably only good to about 2 if we really kind of figure it out, but I'll let it go out to 3. But you end up getting 9.25 times 10 to the minus 5th molar. And that's glucose initial. Okay, so what that is that's the initial concentration of your glucose. Okay. Now, that's going to be the same for everybody because everybody prepped this exactly the same way. So you don't really, I mean, you can show me that calculation in your notebook, but it ought to be the same for everybody. All right. So again, what do I need now? Well, I need concentration of glucose that remains after each time, right? So that's that thing that we basically set up here. So now I have this part, right? But now I need to have the concentration of the glucose used. Now the deal is that part's going to change as we go through the experiment, right? Because we're using up glucose as we move through the process of the experiment. Okay, but now how do I actually measure the concentration of glucose that I used? What can am I actually measuring the absorbance of the glucose itself? What am I actually measuring the absorbance of? Anybody remember?
The hydrogen peroxide or the protonated, the reduced agent. I forget what it is.
Yeah, it's that O-dianisodine stuff, right? So in this case, we take it all the way to the orange form, right? So it's, I believe, the oxidized form, but then we don't actually add the acid to it and protonate it. So it's that nice orange stuff. So I think it ends up being the O-dianisodine oxidized is what we actually have. So basically what we're doing is we're relating the glucose concentration to the O-dianisodine concentration, because that's what's actually doing the absorbing, right? That's the colorimetric thing that's coupled to the glucose reaction through the hydrogen peroxide. But what did we say about all those mole-to-mole relationships? What were they? Well, they were 1-to-1 all the way through, right? So ultimately what we can say here is that the concentration of the glucose that got used is equal to the concentration of the O-dianisodine, which I'll call just O-dian, that got formed. And that's that orange form of the O-dianisodine. And it's all 1-to-1 throughout, so it doesn't really matter, right? So now this comes back to the question that I think John was asking a little bit earlier, is now how do I deal with that, right? How do I get at that? So if I can talk about this in terms of a concentration of O-dianisodine, right, then I've got the concentration of the glucose that got used up, because the glucose that got used got converted in a 1-to-1 mole relationship to the O-dianisodine. So here's how I do it. I'm going to say that the concentration of the glucose at time t, that's what I'm trying to get, is equal to the concentration of the glucose at time 0, which I have, right? We just calculated that. That's this number right here. So that never changes. That just goes right in here. Minus the concentration of the O-dianisodine formed. Now, that I can put in terms of Beer's law, can't I? I can say that concentration is equal to the absorbance that I measure divided by epsilon times B. That's just Beer's law solved for concentration, isn't it? In terms of the O-dianisodine, because that's what's doing the absorbing. So now what I can do is subtract that term, A over epsilon times B. Okay, now look at that term and tell me what's changing and what's constant. Okay, what's B in this case? Well, that's just the path length of your cuvette. And you guys measured that last week. What was it? It was like 1.10 centimeters. I think that's what you guys came up with. Okay. What about epsilon? Is that a constant or does that change through the course of the experiment?
That's going to be constant.
Yeah, that's a property of the O-dianisodine, right? So that's constant. That's constant. So what changes? Absorbance. And that's what you measured, isn't it? That changes with time. Why? Because we're using up the glucose and we're converting it to O-dianisodine. So what's happening? Well, the O-dianisodine concentration is increasing. So the absorbance that you're measuring also increases. Okay, you probably noted that as a decrease in percent transmittance as the experiment went along its merry way. Okay, so now what I've got is an equation I can use to get glucose at time t. What's the only part of it I'm missing? What's the only part that I need? I've got numbers for pretty much everything except one thing. This gets back around to what John was trying to.
Yeah, the molar absorptivity.
Yeah, you need the molar absorptivity. That's the deal. You need the molar absorptivity. Okay. So you need the molar absorptivity for O-dianisodine here. Okay, so we're going to go back to Beer's law here. Okay, so we're going to assume that the reaction has ended at 30 minutes. And again, the assumption that I have to make is that 100% of the glucose has been converted to O-dianisodine, right? So now I can use Beer's law to get back at the epsilon. So this is all for O-dianisodine here, is equal to epsilon times B times C. Now I can solve that for epsilon, can't I? So epsilon is equal to the absorbance divided by the path length times C. Okay, so if I'm assuming that I've got 100% conversion of glucose, okay, do I have a concentration for O-dianisodine now?
Yep, you solved for it earlier.
I solved for it earlier. What do we say it was? 9.25 times 10 to the minus fifth molar. Because that's the initial concentration of the glucose we had, right? So if we assume 100% of the glucose has been converted to O-dianisodine, well, then we've got that concentration. Do I know B? Yeah, B hadn't changed. That's still 1.10 centimeters. And what about A? Which A do I use here? What A should I use? It's an A at a certain time. So which time should I use?
Is it the last one that we take?
Yeah, at T is equal to 30 minutes, right? That's as far as we went. Okay, so use the absorbance you took at 30 minutes because that's assumed to be the absorbance that corresponds to that concentration of the O-dianisodine, which is 100% conversion. So now I've got an epsilon, right? So I can take that epsilon and I can plug it back in up here, okay? So now if you look back at that equation, which you can now set up in Excel, right? You got the initial glucose concentration, you got the epsilon, you got the B. The only thing that's changing now is the absorbance, right? So now it's very simple to go into Excel and set this up. So I would do it exactly the way I talked about before. Don't do this by hand, guys. Let Excel do this for you. Let the Excel do the work. Okay, so you can set up an equation, okay, where you start out with an absorbance, right? So you list your absorbances, okay? And then in the next column over, now you could actually do this calculation, couldn't you? So put numbers in here, program this formula in. And now as the absorbance changes, you'll get the corresponding glucose at time T, okay? Then once you have that, then use it to plot your data out 3 different ways. Once you have glucose at time T, well, then you can take the natural log of it. Then you take the inverse of it, right? And then you'll have all the data you need to be able to make your 3 plots and figure out which one is most linear. Okay, does everybody kind of see how that works?
Yep.
Yep, so that's what we're going to do. All right, so here's where I need you guys to give me your opinion, all right? My original thought had been to kind of go over this today and kind of give you a roadmap, which I think we've kind of done here. And then my original thought had been that next Monday, we could actually meet face-to-face in class, and you guys could bring your laptops with you, and we could go through this, and that way you could kind of help each other out if folks ran into trouble. Now, this is the way I've done it in the past. And a lot of that's because, again, we use the plate reader, which gives us a lot of data to have to deal with and sift through and figure out what to do with. Now, you've simplified things considerably by using the Spec 20. So your data workup is going to be actually a whole lot easier than it normally would be. Okay. So here's my question to you guys. Do you guys still want to do that? Or do you feel like you're good enough just to kind of go off on your own and do this? Because if you feel like you're good enough to go off on your own and do this, then I'll just pick up with the redox chemistry and all that kind of stuff on Monday. So it's kind of up to you which way you want to go. What are your thoughts?
I feel like since it was made a lot easier just by using the Spec 20, that it'll be easier just to do it on my own.
Okay. I think that's fine because I don't really want to lose a class period. In other words, if we did this, I'd want to feel like it was useful to everybody instead of just 2 or 3 people. So my druthers is that I don't see any reason to meet. And I also know that a few of you guys live far away and you'd have to make a special trip in to do this. Okay. Which would probably not be terribly convenient. So I think what I'm going to do is I'm just going to go ahead and do my normal introduction of the next experiment on Monday, because I think we've pretty much gone through enough of the roadmap with this that I don't think you're going to have any real problem doing this with Excel. And of course, if you do, you can ask me, right? Or ask each other or still help each other. I think it's perfectly fine to do that. But I think the experiment's a lot more straightforward from the Excel point of view than it otherwise would have been. Does that seem reasonable?
Yep.
Yep.
All right, perfect, perfect. So really, I mean, that's about all I wanted to go over today. So, I mean, you know, unless there's anything else you guys want to talk about, I'm pretty much done. I think that's everything you guys need to know to kind of move forward with the data workup on the experiment. Anything else, guys? Hearing none, then I think we're done for today. You guys get out a few minutes early, which is fine by me. That doesn't happen very often. Guess it makes up for all those days I kept you guys an extra 5 minutes, right? Okay, so you have a rate of rest day coming up on Friday, right? So everybody enjoy that. I'm actually gonna go back to Virginia and check up on my sailboat, make sure everything's okay, see my mom. You know, it's first time getting out of here since like October, so I'm looking forward to it. I'll be drinking martinis out on the porch. I don't know what you guys will be doing, but that's what I'm going to be doing.
Not that.
Not that. All right. Fair enough. All right, guys. So again, as you work up through this, if you have trouble, let me know. I'll be doing regular office hours tomorrow. I'll be doing regular office hour on Monday. Get up with me if you're having issues. Another thing just to mention real quick, I have been working up accuracy and precision data. So I have accuracy and precision data for the gravimetric analysis. I've also got it worked up for the EDTA analysis, the calcium. You'll also have it for the Spec 20 experiment you did with the iron, and you'll also have it for this experiment. Now, I'll be trying to get that back to you in the next week or two. If I don't have data for you, it just means that I don't have corrected data. I know I asked some of you guys to get me corrected data for those experiments. I've tried to get that back to you. And if I don't give you scores, that means I just don't have data for you. Okay. So that'll let you know which experiments you're missing data for or need to do corrections for, or whatever the case. Okay. So that'll kind of give you the heads up of anything you need to revisit, because I can't really give you accuracy and precision scores until I have correct data from you. Okay, so I'll be starting to turn that back probably next week. So you sort of know where you stand with that. No, a couple of you guys have asked me about that, and I've been kind of holding out, waiting for some data from people, but I can go ahead and start getting that back to you. So I think that's the last part of the puzzle for you guys as far as graded work coming back needs to happen. All right. That being the case, I'll see everybody next Monday. If you have any issues, just give me a call, or, you know, when I say give me a call, hit me in the office hours. All right, guys, have a good break for what it is.
Then I got a quick question. You said that was what you had to worry about, like graded stuff, but we have final, formal reports. Which
I haven't
I'm not
decided what I'm going to do with that yet. I may skip it.
Okay, so would you just then scale everything so it would be like the same amount of weight or?
Yeah. So all I
Okay.
would do is I would just eliminate that and your 100% would come from everything else. I haven't
Okay.
decided whether I'll do that or not. It's really just an abstract. That's really all I have you do. So
Okay, and
I may
then
keep it in just so I can teach you how to do an abstract. We have enough time to actually get that done.
okay. I know I shouldn't be worried. I just missed too many points that I like to be. But you don't have a grading scale here, so I was curious if I could prod at that because you have the percents but no scale, or is it the
Yeah, I
normal
leave this.
scale?
I leave the scale blank for a reason, and that's because when you tie everything together, a lot of times with accuracy and precision and everything else, the highest score might be like an 85. And I like to be able to call that the A.
Okay.
So that's
So
why I don't put a scale on there.
so even though I miss points on quiz, it doesn't mean I'm gonna get a C.
I don't think you're on a C trajectory.
All right, I hope not, because yeah, that would not be good. Okay, sweet. Sorry to bother you about that so much.